What you are seeing right now is one of the most ambitious projects on Earth, located under a cap secured by these bolts. That is the deepest hole humans have ever drilled. It is the Kola Superdeep Borehole. It is 12 kilometers deep, with a mouth just wide enough to fit a dinner plate. It took the Soviet Union 20 years to drill this super deep well. During that process, several unexpected scientific discoveries were unearthed. Today, many nations are also attempting to drill to find treasures hidden underground. Once successful, it will push humanity to break free from dependence on fossil fuels. So, what exactly are those treasures? Actually, at the Earth's core, there is a natural reactor and nuclear fission. Its temperature is 6,000 degrees Celsius. Just tapping into 0.1% of that heat would be enough to meet all of humanity's energy needs for 2.5 billion years. However, harnessing this heat is not easy. Currently, only a few countries possess favorable conditions. For example, Iceland has geothermal sources near the surface. In areas like the Ring of Fire, other nations that want geothermal energy need a way to drill for it. For every kilometer drilled deeper, the temperature increases by about 30 degrees Celsius. When the temperature reaches 374 degrees Celsius and the pressure hits 22 megapascals, water turns into supercritical fluid. This supercritical fluid has some superior properties. It can operate steam turbines very efficiently. However, with current drilling technology, it is almost impossible to reach the depths required to create supercritical fluid because drilling costs increase with depth. Drilling about 3 kilometers deep already costs several $1,000,000. At 6 kilometers, the cost multiplies many times over. When drilling deep, high temperatures damage the drill bit, making it difficult to penetrate rock. Replacing a drill bit requires pulling the entire drill pipe up. The deeper you go, the higher the time and cost. For this reason, a U.S. company, Quaise Energy, came up with a bold idea. If you drill without touching the rock surface, the drill bit won't get damaged. Therefore, they invented a machine that uses high-frequency electromagnetic waves to vaporize rock. The operating principle of this machine is to create an electron beam in a vacuum, accelerated through a powerful magnetic field. Here, the electrons orbit the magnetic field and achieve resonance. From there, a large amount of electromagnetic radiation is emitted. This principle is similar to a laser, but instead of visible light, it creates high-frequency microwaves shot out from a waveguide. First, it melts the rock, then it vaporizes it. Next, the vaporized rock is sucked up through a tube. This machine will drill down at a speed of about 70 meters an hour. At this speed, it takes at least a few dozen days and a large amount of electricity to drill a 1-kilometer deep hole. Calculated at $75 per megawatt hour, the electricity cost alone would be $75,000. Currently, this company has raised $90 million to prepare to prove this technology is feasible. If they succeed, it could propel humanity to quickly escape dependence on fossil fuels. This is a massive mechanical pile driver with an iron hammer weighing up to 10 tons. The machine operates without any electrical system, yet it can still lift the iron hammer easily to drive giant concrete blocks into the ground. So how does a machine without electricity easily push a heavy iron hammer down onto a pile? Look at the principle and you will understand immediately. You will admire this genius idea. First, at the bottom of the hammer, there is a sophisticated design, a hollow steel tube structure. This is the guide joint for the up and down movement of the hammer. Before the pile driver starts, the operator lifts the hammer to a certain height. When the hammer is lifted, the inside of the steel tube is filled with natural air. Conversely, on the bottom part, there is a protruding component, the piston. When the hook holding the hammer is released, the hammer falls due to gravity. When the hammer hits the bottom part, the two parts mesh to form a cylinder chamber. At the same time, the falling hammer causes the air in the cylinder to be compressed rapidly. This compressed air contains a huge amount of energy. It will assist the fuel in generating powerful mechanical force. This is thanks to a fuel injection system hidden inside the bottom part. When the air is compressed to an optimal state, the system immediately injects fuel. Due to the compressed air, pressure and temperature rise.
Therefore, under the compressive impact of the hammer, the temperature in the cylinder rises sharply. Consequently, the fuel injected into the piston is ignited. Next to the piston is a fuel tank. Inside the tank is a high-pressure pump controlled by a lever. In short, you just need to control the pump lever and fuel will be pumped out. And the component that controls that lever is an impact pin on the hammer. When the hammer falls, the pin performs the control action, trips the latch lever. When the hammer leaves the control bar, it automatically returns to its old position. When compressed air and fuel mix and are ignited, an explosive reaction occurs in the cylinder, releasing a large amount of thermal energy, thereby creating a powerful thrust. This force causes the iron hammer to be pushed back up while the exhaust gas in the steel tube quickly escapes. Then, fresh air is brought in to prepare for the next beat. If you want to stop the machine, simply turn the oil pump lever to stop injecting fuel. This is the massive high-tech mechanical pile driver.
Do you dare to believe it? 2,000 years ago, when there were no engines and no springs, Cetebus used only water and the principle of water-level equilibrium to create a complete automatic clock, which even doubled as a calendar. It was born 1,900 years earlier than the Chinese water clock tower. How on earth did he do it? Thousands of years ago in ancient Greece, they initially relied on sundials to calculate time. But sundials had a drawback. They couldn't be used when it was cloudy or raining. Later, the primitive water clock appeared. The method was very simple. Use a large jar filled with water, then drain the water from the bottom to start counting the hours. Of course, time markings were carved inside the jar. When the water dropped to a certain line, it indicated how much time had passed. To stop it, you just had to plug the hole. However, the problem that arose was, as the water flowed, there was less of it, so the water pressure decreased, causing the flow rate to slow down, making the timekeeping inaccurate. Therefore, people stretched the distance between the markings at the bottom of the jar to match the changing water speed. Doing so increased accuracy slightly, but problems remained. First, eventually, the water would run out. Would you force someone to refill it all day? Second, this method was just a timer, not a real clock. So an automatic water clock had to solve three problems. First, stabilize the water flow so time is consistent. Second, it must automatically refill the water, eliminating the need for manual pouring to be convenient. Finally, it must adjust for the time difference between seasons, so the length of each hour changes according to the day-night ratio without deviation. It should be added that today the duration of an hour is fixed, but in ancient Greece it was not. They divided the time from sunrise to sunset into 12 daytime hours. In summer, the days are long, so an hour could be longer than 60 minutes. In winter, the days are short, so an hour might be only 50 minutes. Therefore, the markings on the water clock had to be adjusted according to the season. Now comes the important part. How did Ctesibus's water clock achieve those three things? This is its core component, a vertical cylinder column engraved with a scale of 12 months and 24 hours. One rotation of the cylinder means a year has passed. On this bar is a pointer used to indicate time, attached to a float placed inside a cylindrical container. A reservoir next to it feeds water into that cylindrical container. When the float rises, the time counting begins. Note that the stable water flow relies on the external supply tank. Water is continuously replenished from above, and excess water flows out from an overflow pipe, helping the water level remain fixed. The flow rate is constant thanks to constant pressure, making the measured time accurate. As long as the supply tank has water, it is enough. But what if the water fills up after 24 hours? How does it automatically restart and count from the beginning? The secret lies in this U-shaped siphon tube, truly an automatic reset miracle from 2,000 years ago. When the water level in the tube reaches the top, gravity causes the water to flow out at the outlet. The vacuum effect created helps drain all the water in the container. You can drain it all without touching it. The next day, it can start counting again from the beginning. Finally, one more thing had to be solved. The length of each hour had to change according to the day-night ratio of each season. They placed a water wheel at the siphon's drainage point. It has 6 water compartments. Filling one compartment rotates it 1/6 of a turn. The water wheel connects to a gear set, and this gear set pulls the cylinder column engraved with hour markings. The gear ratio is calculated extremely precisely.
The water wheel rotates 1/6 of a turn per day, so the cylinder rotates exactly 1/336th of a turn. 1 year fits exactly 1 rotation. The timelines on the cylinder are adjusted to curve according to each month, perfectly matching the change in the length of each day and night. And just like that, an automatic water clock that even integrated a calendar was born as early as the 3rd century BC. It wasn't until 1656, when the pendulum clock appeared, that it was surpassed. That means it was born 1900 years earlier than the pendulum clock. Now you understand, right?